Welcome to this session, and we are going to proceed with another example, which is example 3. And in this case, the unique thing about this circuit is that this time we are given the current as the source. And being given the current as the source, then we look at it critically. We are supposed to create a short circuit current across this device here, so that we get what we refer to as I of SC. So getting the short circuit current, I of SC. When we have created a short circuit current, short circuit path here, what do we have at the look at the circuit? The current that gets here will be bypassing all these resistances. When you create the short circuit at this point, the current because all these resistors are in parallel. So at the end of the day, the short circuit current I of SC will be 40 at the angle 30 amps. Then we look in at the point of the short circuit by looking in. We determine the Norton's internal resistance. And we shall have our circuit appearing this way. We shall have a circuit. The circuit will appear as this. In this case, because there's a current source here, we replace it by an open circuit. And replaced by an open circuit, we shall have the conductors hang in this point because there's no continuity of path. So we shall have. We are not going to have that in the analysis of the internal resistance. And by so, then we shall have this. Then Norton's internal resistance. The resistors here are in parallel. We shall have the product of 4 into 2 plus J4 over 4 plus 2 plus J4. We shall have this as 8 plus J16 over 8 over 6 plus J4, which is equivalent to, we change this in polar. This comes 17.89. The angle is 63.43. Over 6 plus J4 6 the angle J4. Shall have here a 7.21. The angle here is 33.69. So we divide the magnitudes and we subtract the angles. 17.89 divided by 7.21. It's 2.48. The angle is 63.43 minus 33.69. 29.74. ohms. So we have that as the Norton's internal resistance, which is given abbreviated as Rn. So from there, we're supposed to do the Norton's equivalent circuit. We shall have our current source being the short circuit current. Then we shall have our Rn being connected in parallel. And we shall have our RL. So this is a RL, which is 10 ohms. Our Norton's is 22.48. The angle is 29.74. The I of AC is 40 angle 30 degrees amps. So I of L is supposed to be the opposite amp is R of N over R of N plus R of L multiplied by I of SC. The opposite amp is 2.48. The angle is 29.74 over the total impedance is 2.48. The angle is 29.74 plus 10. This is multiplied by 5 plus 40. The angle is 30. So we change all this into polar. We change this into polar so that we are able to divide. So changing 10 into polar is changing. We cannot add 10 and 2.48 in terms of polar. We must change this into Cartesian first, then we add. So we go into rectangular form. That's 2.48. The angle is 29.74. This can be written as 2.48. The angle is 29.74 over 2.153 plus J 1.23 plus 10. Then this is multiplied by 40, the angle of 30, which implies that we shall have 2.48. The angle is 29.74. We add and convert that into polar. 10 is 12.153. Shall have this as 12.22. The angle here is 5.77, 5.78. This then multiply by 40, the angle is 30. So when divide the two, 2.48 divide by 12.22. 12.22, then multiply by 40. We shall have our answer here as 8.12. The angle there is 59.74 minus 5.78. This is 53.96 degrees. This is amps. So that marks our load current. And that marks the end of that question. So this is an example of an application where the current is the source. So you take note that anytime the current is the source, when determining the internal resistance, we break the current path, it becomes an open circuit. And by so we shall be able to understand how this analysis is done. Now let us proceed. In this case, let us proceed to example 4 and also look at a unique feature about the circuit. The circuit has got a 4 ohm resistor in series between the two parallel lines and the source. So for us to get the short circuit current, if we create the short circuit path across this, it means that the short circuit path here will bypass the J4 ohm resistor and the 8 ohm resistor. And in that case, we shall have our I of SC across the load. The I of SC across the load, we shall have that as the opposite arm is 6 minus J4. This 6 minus J4 over 6 minus J4 plus 4. This is what we are going to multiply by 5. The angle is 60 degrees arms. We change this into polar so that we can be able to get the values direct. This is 7.21. The angle here is minus 33.69 over 10 minus 4. 6 plus 4 is 10, so it with 10, 4 shall have as 10.77 angle is minus 21.80. This is what multiplied by 5, the angle is 60 degrees. When we divide that, we shall divide 7.21 divided by 10.77. Whatever I get multiplied by 5 times 5, we shall have this as, this gives us 3.35. The angle there is minus 33.69 plus 21.80 plus 60. We get there as 48.17 degrees. So that is the current that's going to be across the short circuit path. Then we have this now arms. Then we have Norton's internal resistance, Norton's internal resistance, Rn. In this case, we have been given a current as the source, and we're going to replace that with an open circuit. So we are going to have our diagram appearing this way, minus J4. Oh, there's a capacitor. By looking in, we shall be able to realize that this is the kind of circuit we are going to have. This is the kind of circuit we are going to have. Then the 4 ohms in series with 6, so we shall have Rn being given by J4 into 4 plus 6 minus J4 over J4 plus 4 plus 6 minus J4. This is what we shall have there. When you look at that critically, we shall have 10, we shall have J4, this is 10 minus J4. Then the denominator here shall have only 10, because critically look at that, you just have to divide. Then you get, that is, you get the polar, then divide. You shall have 16 plus 16 minus J14. So you shall have, this is 16 minus J40 over 10. We can divide through first, then you have 1.6 minus J4. Get that into polar. Already you have done, you have solved it. 10 is dividing throughout. So 10 into 16 is 1.6, 10 into 40 is 4. Then we shall be able to, this is now the ohms that we need to convert this into polar for the purpose of analysis also. We have the equivalent value in polar, 1.6. This 4.31, this is or 4.31, the angle is 68.2. This is ohms. So from after determining the Norton, we draw the Norton's equivalent circuit. Draw the Norton's equivalent circuit. We shall have our current being in that manner. The circuit appears this way, and we shall have our load appearing as 8. This is 8 ohms. And this is 4.3, this Rn, 4.3, the angle is 68.2, 68.2 ohms. So our current source is going to be 3.35, 3.35. The angle is 48.147, 48.17 amps. So the current across the load is supposed to be the opposite over the total resistance times I of SC. Opposite is supposed to be 4.3. 4.3. The angle is 68.2. Over the opposite, over the total resistance, that is Cartesian, 8 plus 1.6 minus J4. This we are going to multiply by the source current at 3.35, the angle is 48.17. Convert this into polar so that we have, that is 9.6. Convert that into polar. We shall have 4.3, the angle is 68.2, over 10, the angle is minus 22.62. This multiplied by 3.35, the angle is 48.17, which gives us what? 4.3 divided by 10 is 0.43. 0.43 We multiply by 3.35. This becomes 1.4405. The angle is 68.2 plus 22. 68.2 plus 22.62 plus 48.17. Shall have 138.99. So that's the final answer. So I hope you have been able to follow the analysis that we're doing, because this is basically applicable to all your division areas, and the areas when you want to turn in the circuit analysis by logical reasoning in the circuit. So we are going to start another topic now, or another theorem, which I refer to as the Millman's theorem. So you refer to your past papers and see whether you can be able to apply this basic knowledge on analysis of networks, and especially the Norton's theorem.